Uh, hmm. All right, let's post that we're live. Da, 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 da. So, scanning the PCI bus tonight, looking for hard drives. Join for some fun. OS Dev. Is it fun? Is it really, or is it just torture? Okay, let's get booted up. Let's grab VS Code, log in to the VM. Just realized I've got my microphone attached. I don't need that. Right, let's kick the tires. Everything running, working okay. Wonderful. So we're going to need a couple of references for tonight's work. We're going to be needing the main page, and we're looking for PCI. I think it's PCI Express though. Let's try this one. Changes from the PCI configuration space. Oh, changes it from 256 bytes to 4K. All right, so we still kind of need to do PCI. So we kind of determined last night that the starting address for this guy is actually in the ACPI documentation. So if I look at the logs, we were dumping the tables. So this found ACPI table MCFG here. So it's this guy that is going to give us the address. So we need to grab the ACPI spec, which is here. And we're going to look for that table name that we found, which is here. PCI SIG, see links under the heading. Oh, we went to a website, didn't we? And then this thing wanted us to log in. That's right. And then we found that on the OS Dev Wiki, actually, it had the tables for us. We could copy and paste in. So does it mention the MCFG in here or the ACPI? Check device, bus scan, IRQ handling. Solaris documentation. Anything in here mentioning the MCPI? Gotta be something out on the web. We might have to find it. So I'm going to look for ACPI MCFG. Hoping someone's going to drop a link to like a public doc. I'm wondering if we should throw a validation on this to begin with. Probably going to do that actually. Because it's a critical thing we're going to put in the kernel. Like you need to have this table, and if we don't find it, we can't start because I don't want to do the port IO stuff. So when we initialize, I'm going to look for this table. Like we do here. Flip that variable to true, and then what we'll do when we've got to here is we'll printf universe table not found, mmio support for PCI. Memory mapped IO support for PCI not found. Quitting. So we definitely shouldn't get this to begin with. That is a weird spelling. I can't. That's in kernel H. Okay. Kernel H. And then run that. Okay. We're gonna capture yeah, so I need a reference to that structure now to be able to parse it. So back to ACPI MCFG table. Stack Overflow, OS Dev. We might need to extract it from somewhere else. It might be in the Klyra source code. See if we can find it in here. It'll be under PCI. Might be in the headers. Device, bar driver. Oh, actually, it might be in the ACPI, which I think is under sys. Oh no, it's got its own folder. Standard description table. It's the RSDT and the RSDP. So this is a method that looks for that specific table. So I bet I can find somebody using that. Hi, Victoria. How you doing? Roast my code? You want to roast mine? Or do you want me to roast yours? I think about 50% of my job as a tech lead is code QAs. No, I'm looking at GitHub because I'm looking for some documentation on scanning the PCI bus. And the official spec, you've got to sign up to a website. And they might even charge for it, but I don't want to go that far yet, so I've got this example of another operating system that a bunch of people are working on open source that I sometimes like to dip into here, but not to copy any code, but to see any hidden pieces of knowledge. I mean, sometimes I have to dip into the Linux kernel as well. So the Linux kernel is absolutely amazing for finding lots of documented gems that has actually helped me. So when I was doing the high performance timer, the Linux source code has got documented a lot of bugs with it that I was experiencing. And none of those bugs were reported on the OS Dev wiki or any of the documentation that I had at hand. Temple OS? No. I believe Temple OS, I think it's a 32-bit operating system. Whoops. Is it 64-bit? Oh, it's 64-bit. Single address space, ring 0, so it doesn't do any privilege stuff. That might be another good source to check, I guess, if it's a 64-bit OS and it's written in C. Why has ring 0 made you laugh? Dare I ask? Because Bible. Okay. No, the rings, excuse me, the rings in OS Dev are the privilege levels that you can put an application in when it's making or executing instructions on memory access or certain instruction sets on the CPU. So you can switch to a different ring and then it kind of puts you in that privilege context to, like in ring 0, you've got access to everything, right? You can dip into any area of RAM that you want. You can execute any instruction. And then you'd probably run your applications in user space in like ring 3. And drivers might live on ring 1 or ring 2. So you can set it up with like different privilege for different purposes. Oh, you know about them, sorry. No, I have really simple humor sometimes. I'm ashamed to admit, but simple immature humor can get to me as well. But you can't just say that. All right, what am I doing? Throwing me off here. I'm looking for this function. I can and I did and I will. And you will like it. All right, here it is. So it's passing it as a standard table. And it's checking, doing some validation there to go back to legacy mode if it doesn't find enough information in that table. No, this is VS Code in the web. So when I'm browsing GitHub repos, I don't know if you knew this, a lot of people don't know this, but if you press the period key, like this, period, it opens VS Code. Isn't that amazing? I'd say it was pretty awesome. MCFG entry. Okay, they've got a struct here. We might have to just rip this. Here it is. So MMIO base segment start end and reserved. It's all. I don't feel bad about copying this, but what should have happened was somewhere on the OS Dev Wiki, they should have just given us this struct and told us this was the memory layout at that table address. So we'll just shamelessly rip that structure and put that in our ACPI, which I'll think this will have to go in the header. So this is the MCFG. It's going to be a packed table. You know, I read a tweet from John Carmack. Can't remember when it was. I think it was a tweet around AI, but it could have been another one. But his comment was that he'd worked with somebody who had refused to stop using assembly and to start using the C language. And that person's was so reluctant, like they just wanted to stay with assembly. Now, half of the reasons or half of the bugs that I've had during my OS development experience is that I'm fighting with the C compiler. So when it comes to like really super low level coding, it kind of gets tripped up and you have to pop open the assembly code. So you've got to be prepared to like, okay, what does my assembly code look like? Because you can't trust the C output or the building of your source code. And all the little tricks like these attribute lines and the volatile keyword. And if you look at the Linux source code, it's got a crazy amount of C syntax that you just don't use anymore. But it was all trying to control what the C compiler was doing. And it can get you into a mess sometimes. So you can't trust your C compiler, like what it's doing for you half the time. If you don't know what you're doing, which I don't know what I'm doing. So, hi Neg, nice to see you again. What is it Clion? I've never heard of this before. It's from JetBrains. C Lion. It's a C++ IDE. Yeah, I would imagine, you know, I'm absolutely willing to bet that this is better than VS Code for writing C with, because at work, I have this mode, right? When I'm opening up Go projects or something, if it's quite a small project, because some of our services are like microservice-y, and if it's quite a small service with like, I don't know, 5 endpoints in it, so it doesn't have a lot of code, I'll open it up in VS Code and have no problem. But once I enter a much larger service that houses like 50 endpoints, and I need to do more clever code analysis and refactorings, my go-to is Goland. So I'd say 50% of the time I am jumping into Goland to manage Go projects. It has such a nicer time doing the IntelliSense and the whole, you know, the build events. Yeah, I've got this love and hate thing around Electron-based applications. Like when I first wrote an Electron.js application a few years ago, I was disgusted in the amount of packaging and the height in which your code base is written. And by height, I mean from the point of you writing the code in it going down to the machine level, right? Assembly. It's absolutely disgusting. You know, the footprint of your applications, right? Huge, hundreds of megs. the slowness, right? Because there is inherently a slowness in Electron.js apps. But it's so hard to say no to the cross platform. You know, that's such a high reward that people are like, yeah, Electron.js everywhere because we love cross platform. Is the ID. Wait, it's not single threaded truly, is it? That's a misunderstanding of Node. Isn't it a single thread that handles like the event and then it goes down to the multi-threaded cores? Like it's not completely ignoring like all the cores in the system. It's not like completely clipped from doing multi-threadedness. There's no multi-threads? Are you sure? I thought the event loop was single-threaded, but the things that pull off the event loop are threads, like real threads. I need a picture here. I need a diagram. V8 event queue. Worker threads. Yeah, this might be it. So once it gets past the event loop and you're doing things like on network process file system stuff, those can be multi-threaded. They're not real threads. I'm pretty sure I've looked into this a while ago and determined that it's kind of, it is single-threaded, but not all the time. Anyway. Workers are just spawning another node process. Oh, that's cheating. Isn't that what Python does? You watched the stream yesterday offline? Oh, so you're one of the people that's watching my streams. I've been absolutely amazed at the amount of people that are watching my VODs, and I don't know who it is that's watching them, but there are some of my VODs from a few days ago that have got like 150 views. And it's kind of like, holy shit, there's people actually watching my saved VODs. All the time workers are just new processes because the JS JIT is not multi-threaded and never will be. Problem. Python's GL is much similar, yeah. Yeah, that sucks. Like, that really does suck. Like, there's no other way to explain it, but that sucks. All right, MFG table, MFG entry. God, I hate not running with documentation. I'm gonna ask the OS dev guys. Let's see if anyone's got that documentation. Does anyone have link to an open source doc or the ACPI MC spec? Can you guys see my Discord? Oh no, I think I've changed Discord. No, OBS to not render Discord. Well, my username is just my name now. If anybody wants to add me on Discord, that's fine. Cool. There's kind of a bit of delay when I'm talking in the Discord. I think most of the users are in US time and they're probably at work. Because what I really want to do, well, those are 8-bit numbers, so they're probably quite sane to look at. I'm not sure what segment is. All right, let's just try and cast to that structure and see what we get out of it. So here is where let's add it up here too. So it's the MCFG entry. I think IntelliSense is kind of a bit screwy because I'm in the middle of typing this variable out. There we go. And then we'll cast that to the MCFG entry. Kind of don't need that anymore because we can just do a null check on the pointer. Okay. All right, so someone's tried to be a bit sarky in their reply here, saying that this was the first some people assume like you haven't Googled. It's like, dude, I have. You're like my last point of call. Like my documentation process is something like, okay, I can't find it on OS Dev Wiki. So I'll check an open source operating system. Okay, I'm confused about what I find in there. I'll go and check Linux. If it's not in Linux and I can't discern something from there, I'll Google. And if I can't find it on Google, then I come to Discord. But there's quite a lot of young people in the OS Dev Discord because I think it's a lot of students doing computer science and they're doing OS Dev. And then they come in there and they're like asking all the noob questions over and over. And it probably irritates people. But equally, some of the very experienced OS developers in there are Google engineers. And it's really interesting to hear what they have to say when they get talking about like the OS level stuff that they work on at Google. So it's a double-edged sword, really. Okay, well, now that we've cast to that pointer, let's see if we can just log what's in there. Do we get any sane values? So we've got the bar, which is on you. Again, failing IntelliSense. Thank you very much. So let's have a look at the base, start, and end. That's actually going to be... Yeah, we can render that as hexadecimal, that's fine. I'm going to render that as a decimal. It's only an 8-bit number. Change those. Right, let's see if we get some sane values here. Imagine not using a breakpoint. It's kind of a pain in the ass. Using gdebug with a kernel. So I'd rather just dump stuff in the log. All right, that looks sane. Right? Anyone want to confirm? This is why I need documents and signatures to hook onto. Or I could be shameless and I could copy the validation that's happening inside of here. That is testing the MCFG table though. Oh, and then it's just pushing it into a vector. So MCFG entries, which indicates that there could be multiple tables. There isn't just one. So that's new. So this is where it reads the table. DevSeg segment. Oh, interesting. It's matching that against a PCI device. Wait, someone's telling me it's on the PCI Express. Oh, it is. Silly me. You need to go consume food? Okay. You will not believe what I had for food this evening. Let's see then. So table signature, length of the table, beautiful. This is all standard stuff. And then it's this guy. PCI segment group number is what I want to see explained. What does this do for us? So the PCI segment groups are numbered, and in most systems this is only one PCI segment group, number 0. Note that legacy PCI config space access mechanism number 1, which exists for backwards compatibility, has no PCI segment group field and therefore can only be used to access the PCI configuration space. Must be used to access PCI configuration for any devices in the PCI segment groups. For non-x86 systems, the method varies, but usually systems provide themselves with a device tree. Oh, I guess that's what we're doing. no, this is something different actually. Huh. Start PCI bus number decoded by the host bridge, end PCI bus number decoded by the bridge. Okay. So they're bus numbers. And this is a group number. It's used to determine which memory mapped PCI configuration space area to use. So in combination of the PCI segment group and the bus, gets us the starting physical address and starting bus number for that memory mapped area. Once you have the correct starting physical address and starting bus number for that memory mapped area, you would use the following formula to determine where the 4K byte area for a function's PCI configuration space is. So physical address is the starting address, which is this guy. Oh, this takes in a device ID though. Finding devices can be done the same as PCI. Yeah, we might need to go back to this here. Bus device function. What's a device? Why is that being passed in? If we're scanning for devices. It's got a bit cold. Let me just turn the heating on. There we go. Okay. Second way avoids a lot of work by figuring out valid bus numbers while it scans. You need to be able to check if a specific device on a specific bus is present and if it's a multifunction or not. Get vendor ID. Base address registers. What we could do, kind of risky actually, if I did a mem dump around that area that the address is pointing to. Let me just check. Let me find out who's calling this. PCI read. Scan function, bus slot function number. Save temps equals OBJ, the GCC flag may be helpful to check generate assembly. Oh, what does that do? Let's have a little Google of that. It puts intermediate files in current directory. We can try adding this if it's not already in our build scripts. Let's have a look. C flags. We can try doing that. Saw a warning though. Warning pipe ignored because save temp specified. User controllable C flags. Let's have a look what that one's doing. Pipe flag. Uses pipes rather than temporary files for communication between the various stages of compilation. I guess we can just get rid of that then. I mean, that doesn't sound groundbreaking. So in the object folder, I'm guessing it's these I files. So what are these? Is this the like expanded like after all of the includes have been done, I'm assuming? Check the S file. Oh. So this is the assembly output per source file. Is that what that is? I wonder where all that data declaration is. I'm guessing there's a lot of debug information in here though, because we've compiled it with the G flag. I wish I could put comments on these lines. I think when I've done this before, I think it screws it up. Location, alignment instructions. There's all these labels. Yeah, I'm not sure what that's giving me, to be honest. Like how to make use of that. Because what I find interesting in the object dump is I've got a memory location and I've got the function labels where they exist in memory. So if I want to find like that function at that address, and then I can see right there the instructions that are generated for that function. So that's the really handy thing. But this, yeah, I'll look into that some more. It's obviously a format that's, it's not the final output that I'm thinking about. So I just need to read into that a bit more. Um, okay. Where were we? OS Dev. We were looking to see if we could link onto a signature. So what I'm struggling to do at the moment is kind of understanding how to get going with the scanning, like how to turn this base address into something that I think we can start working with. So the more I'm thinking about this is that there are devices connected to the motherboard and they're making claim to an area of RAM. And once you know a device ID that you want to interrogate, you use this formula here to find the location of where that device is memory mapped onto. So this isn't exactly wow, it actually takes up quite a lot of memory. The amount of physical address space consumed by memory map PCI configuration space ranges up to 16 tib. What's tib? Terabytes? That can't be. No. Maybe larger than 256 meg. Assessing a specific device within the space can be as follows. Bus. What's bus first? Bus slot func. You can verify you're seeing your macros. Okay. So it just sounds like I need to learn how to read that output then. But yeah, thanks for that, Neg. That's it's probably going to become handy for sure. So how are we finding devices? There are 3 ways to enumerate devices on the PCI bus. Brute force, checking every device on every PCI bus, regardless of whether the PCI bus exists or not. So this here is a scan. Bus number, device number. Looks at a bus count from 0 to 256 or 255 and devices 0 to 32. and then we're asking it to check a device. And then to check that device, we're looking check function, get vendor ID. I think at this point, I need to understand how to read into the PCI memory area. Device structure, detecting configuration space access mechanisms. Vendor ID command, status, register offset, class code subclass, revision ID. Take particular care that the endian ordering follows the PCI devices, not the CPUs. Interesting. I guess you only need to check for devices for the most part on startup. Yeah, it's part of the startup parsing. So kernel boot up would be like interrogate what devices you've got and then mount them into your virtual file system. But we don't even want to do, we're not even going as far as doing a virtual file system. We are just seeing if we can parse the data and find the device ID. Like, I'd be happy to get that done tonight. It's just finding the devices connected and then dumping their IDs and like their class codes. Like, working with them is going to be another battle in itself. PCI specification defines the organization of the 256-byte configuration space registers and imposes a specific template for the space. Figures 2 and 3 show the layout of the 256-byte configuration space. All PCI compliant devices must support the vendor ID, device, command, status, and revision, class code, and header type fields. And implementation of other registers is optional depending on the device's functionality. Um, yeah, I'm missing something here. I'm definitely missing something. PCI Express bus extends the configuration space. 256 bytes of configuration registers for this purpose. Software-driven initialization and configuration of each device or target on the PCI bus via a separate configuration address space. So 256 bytes are allocated per device. So would that be fair to say that using the base address, we can pass every 256 bytes? Is that the PCI Express bus extends the configurations from 256 bytes to 4K bytes? On 8x, okay, so that jump there was kind of what I'm after. It's saying, where did we jump from? Enhanced configuration mechanism. Put simply, the memory address determines the segment group, the bus device function, and register being accessed. Right, so there's a formula. Base address, PCI segment number, start PCI bus number decoded by this host bridge NPCI number. To access a specific register within device's PCI configuration space, you have to use the device's PCI segment group and bus to determine which memory map PCI configuration space area to use and obtain the starting physical address and starting bus number. And then you have to determine where the 4K data is. Note that it may be a good idea to determine the physical address for this function's PCI config space as part of your PCI enumeration, and store this physical address alongside any other information you're using to manage PCI devices and drivers. Also note for the absolute maximums. Okay. How do you know that you're on PCI Express and not on PCI Express though? Does it mention it at the top? Hi there, Tink. I need info. Is there a way to make SRAM 48 and DRAM work on Windows? I have no idea what you're talking about. Sorry, I cannot help there. That sounds like a C library function. Is that a standard C library function? Yeah, the fact that that function generates a pseudo random number would have me thinking that's a C library, standard C library on Windows. Yeah, from what I just Googled, I saw lots of mentioning of obsolete, but I don't want to dig too further into that. Because yeah, I have no idea what that is really. I'd have to research it. How do we know whether we're working with 256 bytes or 4K bytes? How? How do we know? They're really obsolete, but then your university basic course. Oh no. Like if I isn't it srand in C? Rand and srand from time.h maybe. No, it's from stdlib. Good luck with that, buddy. Right, so what the scan function bus slot func? Who's calling you? Scan the bus. 32 slots, 8 functions. Who's calling scan bus? Scan root bus, PCI device root, PCI read. Only one PCI host controller, multiple PCI host controllers. PCI detected devices. What's PCI read doing? It's calling the PCI read for device offset. And there's 3 versions of that for 1, 2, and 4 bytes. So the read word is a 4-byte read. Root dev. Device location. What is device offset? And we've mem set that to 0. Let's just go and dump. So that's the one thing we didn't dump in the log. IntelliSense is failing yet again. Let's dump that segment number. It should be 0. Check that. Segment 35841. That doesn't sound healthy. I'm beginning to feel a bit suspicious. Oh, you know what the problem is? I'm suspicious about those values, and I think I understand why. Because our entry here is the extended fields, and it doesn't have this structure inside of it to offset those fields. There we go. Now it should make more sense. And then we'll check the log. All right. Segment 0, start 0, end 176. Ooh, that address doesn't look happy though. That doesn't look happy. Let me just double check on... Where did it have... Here we are. So I just want to cross-reference this on my other monitor. Boop. So, system description. We've got a signature at 4 bytes. We've got a length of table at 4 bytes. We've got a revision at 1 byte. A checksum at 1 byte. We've got the OEM ID at 6 bytes. We've got the table 8 bytes. Revision 4 bytes. Check. Creator ID 4. Revision ID 4. And then there's 8 bytes reserved. So let's skip those reserved bytes. And now we're into the offset length. I don't think I can have here reserved 1, reserved 2. 4 byte reserved, yeah. It's a good job I checked it. There was that 8 bytes that were in the way. Okay, there we go. So we've got an address here, look. That's now valid. I don't know if you can see that. It's got the word B in it. The letter B in that address. And segment 0, start 0, end 255. So I'm going to go with that as being our valid entry. So it's telling us there are 255 bus addresses. Yeah, the end also makes sense now. Start PCI bus number and end PCI bus number. So I think what we can start doing now is piecing together the addressing formula. So this is where on the PCI documentation, oh, interestingly, look, they have the read word helper function to help you get to where you want to go. Oh, that's the old port stuff though. So hold on, what am I talking about? Where do I want to... Losing track again. Base register. Check device. Right, before I do this, so we need to get a new module going. Let's call this PCI. And I'll grab copyright. And then we'll create the include. And then we'll grab this, grab that in there. Let's call that PCI. Do an endif. And then we'll do a PCI init function, because all of our modules have that pattern. Doop de doop. Void PCI init. And then we'll probably bring in string here because we want the string prints. And then we'll plug that into the kernel. Where does that live for PCI scanning? I guess it can come after the LAPIC. It doesn't really depend on anything other than the ACPI being initialized. All right, so let's start with these kind of placeholder functions. So check all buses. Starts with the bus number. Going to need standard def for that. And standard int, rather. Show me how you compile. Sure. I open the terminal and I type make. And then you're probably going to ask me, what does that do? So that then looks at this script file called the GNU make file. And it executes all of this stuff here, which are compilation commands. So like make a folder, that's the linker, that's compiling C files, that's compiling assembly files, so is that one. Yeah, and that's it. And there's a bunch of settings up here. The flags that pass to the tools are defined above. And this was all taken from the OS Dev Wiki as a, it's kind of been like a starter template, and then I've extended it, if you like. Yeah, and I've got some run commands in there as well. So I created these custom build scripts that build the, so that's the compilation, right? So that's step one. And then the second step is these build scripts that actually create the OS image. VS Code is in Windows, yes. So my VS Code is in my Windows host. And it's remoted into the file system of the VirtualBox using SSH. So the file system on the left here you're looking at is what's inside the VirtualBox. That's not my machine. And this terminal that you see is not my machine, it's the VirtualBox machine. So this is Debian. And again, all these commands are being run on the VirtualBox. So yeah, I've got this then. So after the compile, you've got this build script, and this build script is what's formatting the hard disk file using these SGDisk tools and M format to piece together the hard disk image. And I've got one for an ISO as well, which produces a CD-ROM ISO. So you can also build and attach as a CD, basically, or an ISO image, which is read-only. So, and then the run command, also in the makefile, is what's invoking QEMU. So this here is saying launch QEMU, some standard startup parameters like how many cores do I want to give it, how much RAM, and then I attach the CD-ROM and the ISO image to it. I activate things like the serial port. I create a log file based on the current date time, which is what you see in the log files directory here. So again, this is all custom setup. This is not found in the OS wiki. This is a rolling log file at the time that I launched the kernel. So I've got a log file per run. What else is there? And that's it. So yeah, the makefile. So the run command is what's just invoking QEMU. So make run, and then bam, QEMU is running. I've got a make dump, which is handy. So this is what's making an assembly output from my OS image. So it takes the compiled OS kernel and produces an assembly dump of that entire image, which you've seen me dipping in and out of for verifying what instructions did it output. And then recently I've just added make debug, which is firing up QEMU in debugging mode. And then it waits for gdebug, which is the remote debugger, for you to step through the code line by line or set breakpoints on the code and use it that way. So yeah, most of these again, they're just custom scripts that I put together of how I wanted to set my build chain going, if you like. What the Lamini bootloader gives you is it gives you all these raw commands and tells you, here's all the raw commands, you do whatever you want with them. So it's up to you how you build your compilation chain. And I decided to make it all make driven. So it's just easy to run stuff then. But yeah, there's bash scripts, other build ISO and build hard drive. And it's all on my GitHub if you need to reference it, by the way. So if you need to inspect the makefile and or the build scripts, there's even a README. It tells you what tools I installed on the OS to get it going. So there's mtools and this guy here that help build the image. And then there's an init script what initializes the download of Lamini from that Git repo and builds it and then places that binary in a temporary folder that I keep injecting into my kernel image. Chili Pepper has entered the building. You are a green pepper today, Chili. How are you doing? Good to see you, my guy. Okay. So that's the build, if you want to get going with that. Back to riding this check all buses. So I tell you what, just so you guys aren't in the dark here, what I'm doing, I'm kind of just copying this pseudocode in hope that things begin to click. So we're doing this like full-on brute force scan. And what this is now giving us is that we've got a bus and a device code to plug into the address finding function that we're going to be making as well. So what I'm guessing is, and you probably have all read this before I've even mentioned it, is that we're just going to dive into the memory location where these devices are, where these buses are defined, and start testing to see if there's a device there. And then if there is a device there, we're going to dump out the things like the vendor ID and the class code and see if we can then just start to see our devices connected in the emulator, which I'll be super happy with. I'm always happy to just get going with the memory mapping locations to begin with. Yeah, so there's 8,192 iterations in that for loop, which is a blink of an eye, plus the latency of reading the registers in the memory mapped locations. So be interesting. Check device, bus device. Right, so it then calls this check device function, passing in the bus and the device. So we'll get this created up here. Check device. UINT 16. And a UINT 8, I believe, for the device number. Are you a software dev too, Chili? Or are you a student? Are you in uni? Or both? Are you in uni and also a very experienced software developer? You're a noob? I think we're all noobs. Pseudocode. Get vendor ID, check function. What's that check function doing? Is that just a placeholder to say like, here, do shit with your device? So it starts with this check function with being 0. Then it checks the header type, and if it's a multifunction device, it runs a for loop 8 times, calling the check again for the other remaining values, 1 to 7. Even after 25 years in the industry, I'm still a noob. Yep. Same rep. And what you sometimes forget is the human memory's behavior. So, like, you've only got a window, a detailed window of what you're dealing with in tech in like the last year or so. So things I was doing 2 years ago or 3 years ago have become hazy. So things 10 years ago, I remember what I was doing back 10 years ago, but I certainly am not fluent in detail as much as I would be back then. So my immediate kind of like recent memory window is all based around this OS dev project and all of my Golang and .NET experience at work. But even that memory sometimes like fails me. Like if I go off work for a couple of weeks, I'll forget my Git commands, and I have text files all over my work desktop that I have notes and things that I have saved to remember and remind myself of certain things I need to run in my job. But yeah, your memory window, a lot of people just seem to forget about that too. So what we've gathered from this then is that this check device is basically testing whether you're dealing with a multifunction device or not. So we'll write this in. Again, we won't be doing much because I'm willing to bet we don't have multifunction devices. Get vendor ID. I'm guessing this is a register read. And obviously we can't do that yet. Or can we? Because we really need to do it actually. Because it's doing this check here that's failing the function. So that's how you check whether a device exists there or not. I've forgotten more than I know. I love that phrase. But it's kind of another thing happens though. Like for example, I was involved in a meeting today at work, and though I don't talk about design patterns very often in my work anymore, so like 10 years ago it was all about Gang of Four. I could talk about strategy patterns and visitor patterns and factories and singletons and all those interesting patterns, but we don't really do them much anymore. Or rather, I don't use them by name. Like it's just kind of second nature on doing those things in a code base. But I found in a meeting today that I suddenly launched into a discussion about those pattern names, even though I'd not remembered them for years. Like hadn't had a discussion about them for years. So sometimes that memory does come back on request, which is kind of nice. Basically, what I'm trying to say to you all is that we underestimate ourselves, okay? And everyone's pretty awesome, and sometimes you just forget how awesome you are. Right? Good. Okay, so we've got this check function, bus device function, and this guy, this is a very weird name. We're going to change this check device and check function stuff, but for now we're going to roll with it. Again, we're just fleshing out the pseudo scan, So what we still don't have is a way of reading the memory mapped locations. Bus device and function. That's a UN8 as well. So I'm assuming this is a 16-bit value. To do stuff with the device, because there's a device present here. So we get to that point when there really is a device present and we want to do stuff with it. This thing here is kind of like just invoking that thing, depending on how many functions there are in the device. Check function, header type equals get header type. So again, there is two reads that we've got to implement here for the vendor ID and the header type, which we'll do shortly. Some bracket shizzle there. It's a multi-function device, so check remaining functions. Again, I don't even think with QEMU that we're even going to get anywhere near this loop, because we just don't have these kind of devices connected. But whatever. So again, it does this check up here. It's testing for that magic value of not present. And then we're doing this check again for this bus number, this device number, and that function number. All right, so we've got two reads, get vendor ID and get header type. Is Martin in a super happy mood? Am I? I'm usually quite a low energy person at the end of the day, which is kind of bad for streaming. But I kind of figured for developers, you kind of, realize that a lot of people are just low energy when they're deving. Like zombie mode. And people would still find it interesting even if I was low energy. You can't ban the channel owner. No, Fly Mario, you can't. Another reason why I'm in a good mood, Chili, is because I'm just feeling genuinely happier about the state of where we are in the OS. I've got past the annoying bugs that were getting me down with the timers, and I'm kind of excited again. Getting into hard disk reading to me sounds pretty fun. And I also had a lot to eat before I started the stream, so I'm feeling pretty fed and energetic. Lily seems sad. No, I fed her too. So, Lily the plant was fed today with plant food. I did that before stream as well. Are we still sticking to Sea Lily? Absolutely. 100% we are. It's one of those things that I'm trying to beeline towards. Like, as soon as I can get to work on starting the language and thinking about making a compiler for it, we will absolutely do that. I have even been researching on the strategy of language parsing, like the grammar, and breaking that up and tokenizing it and things like that. So I'm trying to get myself mentally ready for the systems we need to implement to do it. And I've tried this many years ago, but did absolutely nothing with it. So I'm kind of excited to know that now that I have knowledge of knowing how to run binary assembly code, right, and load it into the CPU, I can load programs into RAM. I can tell the processor, hey, go and start to run at this location. And I know what I put there, and I know that it can start running that code. I'm going to be super, super happy. And even if we have to start with really hello world shit, like here's C Lily with its hello world main function with a single command that writes to the terminal, right? Bingo. Even it will start there, and as soon as we've got that pipeline of things in place, we'll just keep growing it and growing it. It's driving you crazy the way I'm using those things. Yeah, inline braces. I'm just respecting the language. So if you look at a lot of operating system source codes in C, you find that they're using inline braces. So I stick to using inline. Yeah, no problem, Chili. Take it easy, buddy. And yeah, I appreciate you dropping by. It's nice to see you. You're one of the OG chatters of the channel. Okay, so get vendor ID and get header type. That's the thing. And the check function is stuff that we're just pinning for now. Please note that if you don't check bit 7 of the header type and scan all functions, then some single function devices will report details for function 0 for every function. So the check all, which is we've got here, yeah, we've got the check all, we've got the check device, recursive scan. The final step is to handle systems with the multiple PCI host controllers. So that's what we saw in the Lyra OS code. It was doing a check for these multi-host controllers. Start by checking if the device at device 0 is a multifunction device. If it's not a multifunction device, then there's only one PCI host controller, and bus 0, device 0, and function 0 will be the PCI host controller responsible for bus 0. If it's a multifunction device, then bus 0, device 0, function 0 will be the PCI host controller responsible for function 1 will be the PCI host controller responsible for bus 1, etc., up to a number of functions supported. I see. So this brute force scan is kind of crazy. Like, I'm assuming it's going to take a lot of time doing that scan. Inline braces is the term, yeah. So putting a brace on the same line as the statement is an inline brace. We don't need this recursive scan. Configuring PCI to PCI bridges. To configure this, kernel has to forget about BIOS. First scan the root PCI device. Check if it's a multifunction to scan multiple buses. Root bus is always 0. Secondary and subordinate bus acts as a range start end of what buses the PCI to PCI bridge will manage. After this, it's up to implementation. Scan each device, and if a bridge is found, allocate a bus number to it. No, PCI to PCI bridges can have multiple bridges within them. I'm kind of reading this because I saw it in the Lyra OS code. And I'm leaving it in the back of my mind for the moment because maybe QEMU doesn't give us this setup. God, that sounds horrendous. A bridge can manage multiple buses, but that means it spans all the memory of these buses. If device 1 is behind bridge 2, which is behind bridge 1, then bridge 2 will contain the memory area of device 1 plus any other device areas. Supposing the I/O is 4 meg, memory is 16 meg, and prefetch is 5 meg. Bridge 2 will contain those. Take in reference table for the header type. However, bridge... Okay, that's kind of insane. If the kernel does not configure a PCI to PCI bridge, the BIOS will probably do. However, on environments without BIOS, this method is mandatory. Otherwise, devices behind that bridge won't show up. Interesting. Message signal interrupts. Enabling MSI. Don't care for that just yet. So, do we have the function for mapping into that space yet? I don't see this in pseudocode. And there probably is one somewhere. All OSs should be written in C#. That would be beautiful, wouldn't it? C#'s beautiful. Memory space bar layout, I/O space bar layout, base address registers can be used to hold memory addresses. So that's specifics. Header type, status register, command register, common header fields. Configuration space access mechanism 2. Aha! Here we go. PCI config read word on the bus slot function offset address slot function temp create configuration address. Where's the base though? No, that's using the IO call though. So that's strategy 1, which is using the I/O ports. Do we need that? PCI Express introduces a new way to access PCI configuration space where it's simply memory mapped and no I/O ports used. It's described in PCI Express. Lies. Lies. All right, this is the guy. Here it is. We found it. We have found it. The check function can get to the address that we want using that formula. And I think that MMIO starting physical is actually this is in ACPI, and I believe we created a pointer to this. Did we export that though? So we'll export that entry, and then we can grab MMIO base. There we go. Do we? So we're in decimal mode here. I think we've got it. I think this is it. This is the winner. We start at the base. We need to push this into the higher half address, which is in mem. It's in mem. I keep forgetting where all my stuff is. So include mem.h. So we'll get that into the higher half offset to get it into physical space. It'd be cool to see this run on a physical computer. Yeah, that'd be awesome. I'd love to try and throw the image at a real piece of kit. Someone has spent a lot of time on this dock. Yeah. I'm guessing like this is a really core piece of OS dev though, like you scanning the PCI bus. So that's the physical address location, and then all of this kicks in, which we can just piece together here. Put this on a new line. Starting bus. Bus minus starting bus. Oh, I know what that is. It's this number. Device. Just a bit concerned there about? I mean, you know, it may be a good idea to determine the physical address for its functions. PCI configurance page is part of the PCI enumeration and store the physical address alongside any other information you're using to manage PCI devices. Yeah, so all that's meaning is make a struct. When you find a device, whack your device information in there, save the address of the device in there, just so you've got access to it later on. And that'll build your internal tree. So I think what it's getting to here is like, once you finish scanning the bus, build up an internal structure of linking all that device tree. I'm actually beginning to wonder now. You guys thinking what I'm thinking? Like when you scan the device tree is it looking at all of this stuff here? Like, is this the equivalent of Windows scanning the bus? But it can't be, can it? Because it's got processors and printers and shit in there. So bus controllers. I mean, it might be. We might see all this shit. I don't know. We could. Probably. Right, so now that we know how to get to a specific address for all of that stuff, how do we know? We need to implement this get vendor ID and this get header type. So we just need offsets now. So that's the command register. Changes from the PCI configuration space. Base address, secondary. Right, so now we need to go back to the PCI wiki and look at the table. Function header key. My guess would be that you see everything connected via PCI. Yeah, that's what I'm thinking. Or did Windows kind of like just make a device tree and look at other things in the system, like just an information parser? But it's gonna be interesting once we light this up because all I want it to do is it's just gonna dump everything it finds at the beginning. You know, again, going back to this, let's just find shit and light things up and see if we can look at vendor IDs and class codes and find devices. That's the quest that we're on. It shows devices connected via USB or SATA. Yeah, well, even SATA drives and SSD drives are all connected on the PCI bus. So USB might be exposed on the PCI bus as a device that you talk to. I can see that happening for sure. Because it's just an extended port attached on the motherboard that's probably being routed on the PCI bus. Like it's not going through some magical chip or a different way into the processor. It's like, I'm a device, here I am, I live on the PCI bus, and that's how I communicate. I mean, I bet you could even, we're at a point where I could look at a motherboard and look at the lines crafted in the actual board itself, and look at where all the chips are being connected. Like, we'd be able to look at what the front side bus is and the north bridge on the south bridge. Oh, you spent your channel points there, Fly. Nice. I forgot now that you get channel points with the affiliation mode of the stream. Da, 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 da. Do, 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 do. For these cases, the only option left is manual probing. I'm going to cheat here, guys. I've got a feeling what I'm after. I mean, we could try this ourselves, actually. We could do a 32-bit read on that offset and see if we can get the vendor ID. Well, that's a 16-bit read for the vendor ID. And then the device ID is in the next 16 bits. I could even create a struct for that. It wouldn't be good, though. That's another thing about OS deving that I've felt, is that sometimes when you're dealing with an MMIO, there's a couple of styles that you can go with. You can create structs full of pointers. You can create offset constants and just create a generic read function passing in the offset that you want to read. And for some reason, I feel more comfortable having tried both. It feels more comfortable having a very explicit read on an offset. I don't know why. It's not cheating. Yeah, you're right. I feel some kind of guilt, but it's just information, isn't it, right? I'm not copying and pasting their code. I'm just after detailed information. So they've got that line there, that target line here for the, so this is doing like the register read. And they've got that exact line that we've pasted in ourselves. So we look at that push 20, push 15, 12. It's the same stuff. Device bus, ent start, segment. What's ent? Oh, is that the vector selector? Yeah, that's the entry in the entries. Oh, I see. That's the index of the object in the vector. So yeah, they're doing exactly what we've done. Bus minus start. Yeah. Access size. asking you if you want to read an 8-bit value, a 16-bit value, or a 32-bit value, and then it's literally doing the read on that address. And then what I'm hoping for is when we'll do a scan for this function and we'll see if they're using constants for the offsets, and then I can just copy those constants in. But we definitely should implement a similar mechanism, like this check function here. So we'll do, we'll call it, I don't know, what should we call it? PCI read. So we generate address based off those input parameters. And then this access size, so I'm guessing we're going to need to know how many bytes we want to read. And then similarly, we're just going to say, okay, if you want to read, if you want to read 1 byte, we're going to do a register read by converting this decimal address here into a memory address. So an 8-bit read, and giving it that memory address that we've just calculated. And then if we're doing a 2-byte read, we're going to do an int 16. And if we're doing a 4-byte read, we're going to do 32. So this is returning a int 32 maximum size, depending, but you know. So now we can start code docking some of this. And we can say read from the PCI configuration MMIO. It's not MMIO, it's MM space, right? So now that we've got the read, again, we just need the offsets now. So if I look for them doing this read, but they do the read in a clever way, they're doing it through the macro because they've got legacy support. So let's have a look for how they read the vendor ID. This will be in PCI. So if I look for the word vendor, reg 0 vendor ID, 16 bytes. Oh, that's read a 32-bit. So that's according to the OS Dev Wiki documentation, what I'm reading there. Can you read 1 byte? What about byte order? Why can't the size of the address be variable? Why can't, wait. Why can this size of the address be variable? Because sometimes if we look back at the table, sometimes there is a piece of information at specific 8-bit boundaries, like here. There's 4 pieces of information in that 64-bit value there. And in this case, you've got 3 8-bit values. Now you've got 4. Excuse me. This is a better table. So actually, this is the table that we're parsing, this one here, the vendor ID, device ID, status command. So like here, you've got these bar addresses. that are 64-bit, sorry, 32-bit. It's all 32-bit stuff. So you can do a 32-bit read on those addresses. But here you're going to probably want to do a 16-bit read for the vendor ID. Which is why I'm looking at Lyra OS and seeing if it's actually got constants for the offsets, or is it doing hard-coded stuff? So like here, reg 0, what's it? Where's reg 0? PC read 0. Read word, it's reading a 32-bit value there. Offset 0. Reg 2. Yeah, so it's not yeah. These numbers here are, I think, the offset into the table. So what I would do here, I would have liked to have seen like just a bunch of defines saying this is the offset for the vendor ID, this is the offset for the subclass, you know, and but I guess it's whatever. Traverse the caps list looking for PCI capabilities. PCI Express, MSI, MSIX. Yeah, so we're quite close now. So all we need to do is do that device and vendor read, which is this guy. So a 32-bit read, which we can do here, right? And I think actually, so getting header type, actually, where does header type come in? So we're getting device ID, status, class, subclass. Oh, header type's on bit 16 to 23 in the third register. Oh, I see. So the way Lyra is done is it's use this register column as what it's passing into its read function. Da, 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 da. We might change this. I've kind of just been infected by the way Lyra OS has created this read, thinking that it's probably useful that we need a varied read, but what it looks like to me is we can just 32-bit read down all of these registers and just play with the bits, bit shifting to get these values out. For example, if we let's try and do this ourselves so we understand the process mentally. Let's try and implement get vendor ID. And get header type in this pseudo fashion. So let's do bus device and function because we need to pass that to the read function. So what we're going to say here is we'll do a read. We'll get the 32-bit reg and copy the naming convention that Lyra's done. We'll say that's the 0 reg, which it is here, register 0. And we're going to do a read on that bus, on that device, on that function. And we're going to read 4 bytes to get a uint 32, and now getting the vendor ID is the first 16 bytes. So all we need to do is cast that to a uint 16, chop off the bytes or the bits. Why do we need OXOFF? Oh, you're thinking about masking. Right, I see. You're masking the value, where all I'm doing is chopping the bits off. Oh, right. No, I can just... Right, I see what you're saying, actually. Like, let's just do a 16-bit read. Like it's done for us. And then if we do... It feels a bit inefficient to have these split up, and I'll probably change this, but I want to see it working for now. So getting the header type, it looks like we're going to have to do a 32-bit read and then shift it over or mask it. So same action. We'll do a 32-bit, 4 bytes. It's not reg 0 though. Wait, where's the offset? Am I being silly here? And I'm not applying the offset, am I? Uint 32 offset. Offset 0. Offset is that. And then we need to apply the offset to this memory address. So header type is offset OXC. We're going to return, let's return a 16 here. Let's return a uint 8 here. And then I just need to, that's actually not reg 0, is it? That's reg 3. So if I cast this to a uint 8 and bit shift this over by 16 bits rather, we're going to get the value that we want, the header type. Yep, 16 brings that over at the end of the mem, and then casts to an int 8, discards those bits on the left. We're good. Okay, so that's that. So that should all run now, but we're not dumping anything. So in our check function, did I delete it? I think I did, didn't I? So it's kind of like do whatever you want here, but there's nothing much we can do other than, I guess, print the found device at, and then we'll just do bus device function. And we'll just see how many PCI devices we find. So we can't, line 53. What's wrong with line 53? What is your concern about line 53, Neg? Oh, you weren't sure of that casting. I guess, would it be nicer for you to have seen it as a mask? Is that more readable, do you reckon? I'm always quite conscious of these things. I want to know what's more readable. So if we were to extract those bits, then we'd have to do a bit mask of, so and then FF here. Is that 16? Yeah. Is that the mask? Is that easier to see? I'm going to leave that there because I want to test to see if that actually works. Right, let's try and get a compile and see if we can get some logs. So it doesn't like PCI init. Why do you not like PCI init, Mr. Kernel? It's because we're not bringing it in. How rude of me. All right, and we got some type errors. Let's go have a look at these. Unknown type, int 8. What? In str? Excuse me? Excuse me? Yeah, that's kind of bad of me. I should have put standard int in there. That's an include problem. Type of bus defaults to int. Why? Where are you, bus? Comparison is always true. What else have we got? Oh, whoops. That really was pseudocode, right? have we got here? Comparison is always true due to the limited range. Oh, is it because I've capped the bus to 8 bits? To make that go away, I'm going to have to cast that to a 16-bit and then get vendor ID or a underscore. And we have a compile. Okay. So that's a lot of code and that's a lot of assumptions. Let's go. Running. Let's scan that bus. And it looks like we've got a report, and that report is looking good. Ladies and gentlemen, we have just successfully ran the bus scan and found 6 devices. That's satisfying. Right, that's pretty awesome. The fact that we just did all of that. I love that. Now, can I get something textual from that device table? Can I, at least start painting what are you? What kind of device are you? So class code and subclass. Let's grab that as well. So we're kind of in the mode now. We know how to read this data. And again, it feels kind of horrible that all of these are in separate functions for now, but get class code. Da, 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 da. Oh my god, that TwitchCon hype icon is extra Emily. That is hilarious. All right, let's get the class code in. We're doing reg2 this time, and we're going to do a 32-bit read. The offset here is 0x8. We're doing a 32-bit read. We're doing reg2. And we want to get the subclass and the class code. So let's grab subclass first. We're going to take reg2. We're going to bit shift it over by 16 bits. And I'm going to convert that to a uint8. And I'm going to bit shift this one over to get the class code by 24 bits. So let's return that class code. And then get class code. Where's the found? Found device class then D at, and then we'll do class code on there. So if we get some good class codes, we can just check the class code table and see what actual devices we found. Subclass unused variable. You are correct, compiler. Thank you. There we have it. We have a 6, 3, a 2, a 6, a 1, and a 12. Isn't that exciting? So, class table, what do we have? What's all this, by the way? Oh, it's telling you if there's further information. Oh, there's a different layout if the header type is a certain type. I see. Okay, so class codes, here we are. Right, so what are we dealing with? We have class code 6. What is 6? It's a bridge. Uh-oh. Scary. We found a bridge. Do we have a subclass code as well? Oh, we do. Let's dump that. Let's do subclass as well. Let's do %d class code subclass. Get subclass code here. We can copy and paste this guy. We'll call this subclass code. And we'll return that one instead. See, we're doing a double read on the same register is what's horrible there. Just to get two different values. That's why it's not kind of efficient. It's a bit lame. All right, now we've got a better view. We've got the class and the subclass. 60, 30, 20, 61, 16, and 12.5. 6, okay, we've already determined that's a bridge. 60 is a host bridge. And then we've got a 30, which is a VGA compatible controller. Nice. We've got a 20. We've got an Ethernet controller, which we do have. We've got network. We've got a 6.1. We've got an ISA bridge. Wow, that's an old motherboard. We've got a 1.6. Is a mass storage controller. And it's a 6. That's the serial ATA controller. Guys, we have found the hard disk controller, at least. Awesome. And we've got a 12.5 as well. So what's a 12.5? What's 12 in hex? Anyone? 9, 10, 11, 12, XC. Got a serial bus controller, and it is a SMB bus controller. And I have no idea what that is. But it looks like you can have USB controllers, is what a serial bus controller is. Okay, that's cool. We've did it. We achieved our first quest, and that is get a list of the PCI devices. And there they are. If I was really fancy, I could just drop that table of classifications and put those in code, like the textual representations. That'd be pretty cool. We probably need to do that actually. If it's a proper OS and you're going to report on what devices you found, you're probably going to want to tell the user that, hey, I found a USB controller, I found a VGA adapter, you know. So I'm probably going to do that actually. I mean, not the whole table though, because that'd be kind of lame. That's a lot of typing. So there's another code though, prog if. What is that? Prog if. Is that in the table? Oh, it is. Oh, let me just dump that then, because that further explains what the device is. It's on the same line as the class stuff. So get prog if. And where's this on? Register 2. And it's on an 8-bit shift. Prog if. Let's just grab that and put that as a dash here, -%d. Let's call the function to read it, prog if, the bus, device, and function, and then we'll dump that here. All right, let's have a look what that storage controller detail is. Da, 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 da. Brain pause there. Okay, we've got the log. So go back down to the class code table. It's the mass storage controller, and then it's the serial ATA, and then it's A1. It's an AHCI 1.0. What is AHCI? Anyone? A serial ATA Advanced Host Controller Interface. Okay, whatever that does, whatever. It's something, it's a device that we need to learn how to communicate with. How would I... So that pair 610, how would I... Sorry, not 610, 161. 161. Like if I was to print it as a string, would I print mass storage controller dash serial ATA controller dash AHCI 1.0? Is that kind of what we want? Is that what you want from me? Am I not enough for you? Sorry. Can you check the virtual machine config? The only configuration that you give to the machine is on run. So it's this here. I'm very curious though how we've not reported. Actually, that serial ATA controller, it might be a CD drive because I've attached an ISO image. I wonder if that's like the CD drive and there is no hard disk because I've not attached a hard disk. Like I've attached a serial port and a CD-ROM, but no disk, which is the HDA command. I don't think my run HDD works. We can give it a try though. Is that running? No, it's crashed. Booting from hard disk, stage 3 file not found. Have you copied lamini bios.sys to the root? Failed to load stage 3. So that's probably an issue with my build hard disk script. This guy. BIOS install. BIOS install. Install the lamini boot stages onto the image. Lamini bios.sys. ISO root. Oh yeah, it's there. It is there. BIOS install image ISO. BIOS install image HDD. Oh. It's kind of funny. I think I've got create a partition table, format the image, make some directories, copy it over the relevant files. Oh, it might be this. We just kill the image to invoke the rebuilds. I should make a clean command for that. Run HDD. Can't find the files. It's almost like these M copies here are failing because this is what's copying the lamini bios.sys and it's saying literally that it can't find. Have you copied it to the root /boot /lamini or boot lamini? And we've copied it to the root. So do those mcopy commands work? Stage 2 to be located. Reminder, remember to copy in either the root or the boot will fail. Build HDD. Oh, there's an issue. SG disk not found. That might be why. Let's try and do that install. I can't remember the command. The apt apt get, and then this invalid operation. Oh, missed the install command. Unable to locate package sgdisk. All right, where's sgdisk from? Packages gdisk. Gdisk. It's already the newest version. Which gdisk? Which sgdisk? Excuse my Linux noobness here. Do, 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 do. sgdisk, a command line program intended for use in scripts or by experts who need quick and direct access to a specific feature. Interactive text mode program similar to fdisk. Cursors-based interactive text mode program similar to cfdisk. I'll do that offline. So people also ask, what is ATA and HCI, Advanced Phase Controller Interface, or HCI? It's a technical standard for an interface that enables software to communicate with serial ATA SATA devices. This peripheral component interconnect PCI class devices move data between system memory and SATA storage media. Nice. I wonder if the OS Dev Wiki has a very specific driver implementation for HCI. Let's see if it's on here. Oh, it does. There we go. So it's got here, find a controller, determine what mode the controller is in, the registers and the memory structures, port memory space initialization, read the hard disk sectors. And there's an example read function. An interesting way to pull in some longer duration reads. It may be helpful to spin on the DPS bit Yeah, so interestingly, we've got all of this copyable code to interact with that AHCI, which is nice because that puts us really close then to just starting to read from the drive and implementing FAT32. I guess a really interesting thing would be is to see if we can look into the drive and load the bootloader, because that's at a very specific location, and see if we can find the boot signature. That would be a good practice run, unless it's been nuked by the kernel load. Um, command table. Physical region description table. Command header. Damn, it's a bit level structure. God, we're really super low level here, like actually talking to the driver, the drive. Oh, and it supports up to 32 command headers, which are like 32 commands that you want to perform. That's interesting. So it's got like a queue. Thanks for the follow, Drunken Tabard. HBA port volatile, so it's all memory mapped IO. Generic host control capability, interrupt status, port version. Yeah, so here it says like find it at the controller, and once we've got that controller, we can come into here and start talking to it. So our second quest begins here, determining what mode the controller is in, and then boom. Absorbing all of this to the point where we can read and write. I wonder what these interrupts are for. I wonder if it gives you an interrupt when it's finished reading or something. There's another page here. Oh, that's the official spec. Cool. Well, I am going to commit the code for the night. Since we've got a good compile here. I will fix that run HDD offline though. I feel like I just need to install some tools on Debian once I've found out what package there is. But yeah, so PCI devices now scanning. I'm still going to have a read over the PCI doc on OS Dev because I've got a feeling we still need to do something with the bridge. It mentioned something about you not picking up certain devices if you didn't do a certain check. And I want to just make sure we're not missing a trick there. Like we're not missing some data in the scan. Or the brute force scan is actually just like containing everything regardless. But it's something I'm going to double check. But yeah, so that's a really nice milestone, is leaping from the ACPI address into a PCI read and then parsing some of that data. It is the beginning of us being able to write a hard disk driver. Like almost at this point now, if we wanted to, we could just take that address that we found, that AHCI controller, and go ahead and write a hard disk writer. So that's fun. So I'm thinking tomorrow's stream definitely will be getting to the point where we were trying to talk to the drive. So reading bytes from the drive and maybe writing to it, but we'll do reading first. We'll see if we can at least do something really crude and see if we can find like the allocation header table and see if we can find the file names of what we've put on the drive. So that would be a nice start to begin with. Because all of that will be easy to dump. And then we'll at least know, oh, look, we can see the drive and there's the data because there's the file names in the FAT table. And then another part to that could be once we've got parsing the FAT table, we can think about how we dip into the FAT data section or the data memory area and start reading file data, which will be very cool because then, oh my God, we can read files. We'll be able to plug that into the terminal. Once we can read files, we can start creating user space programs, putting that on the disk drive that the emulator loads. And then we can even start adding functionality in the kernel to start loading those user programs. And then finally spinning up the cores, which we've already got in a sleeping state, and loading and running those programs. So we're into a huge treasure trove of features that are coming up to the point where as soon as we've got that hard disk reading, we've got a ton of stuff we can get doing. So I'm excited. I'm super pumped. But yeah, for today, I don't want to burn myself out. It's pretty late, and it is a work week, so I've got work in the morning. So yeah, thanks for being here, everyone, and thanks for watching my noob journey into OS Dev. As you see, it's all pretty rough, and I'm constantly fumbling around documents in the C language, but somehow we are progressing every day. We're putting code into the kernel, we're adding features, and we are progressing every day. So it's cool. It's cool with me. There's not enough OS stream devs streams around. Yeah, I thought that, when I joined the OS Dev Discord, there were two things that stood out to me, that there wasn't a lot of good up-to-date information. So even the OS Dev Wiki is pretty out of date, but it's quite valuable for what we're doing, but it still could be better, a lot better. And even the YouTube content is kind of old. Like it's 32-bit kernels and there's not really much 64-bit kernel stuff out there. So I thought, well, I'm used to Twitch streaming, like I've done it before years ago. And I thought, well, why not just stream it, just for fun? I'm sure people will be interested in seeing me fumble around. and going through the pain points of OS dev. What I might do, it depends if you guys want it, is I could export the VODs to YouTube so we have them forever. So before Twitch deletes the VODs from day one, we can just get the VODs over to YouTube, and then people can at least watch the VODs, you know, and I can label them day 1, day 2, day 3, day 4, and at least put some information around what we did on that day. So that might be something. If you're interested, let me know and I'll do that. And then I could do a stream where I just, like what Fly Mario asked for earlier, I could just go through the setup process and show you guys hello world setup of starting from scratch. Maybe that'd be cool. But all right, thank you very much, guys. Thank you for being here. Thanks for the follows. Thanks for watching. Thanks for your support. You're all awesome. Have a lovely evening, and I'll see you hopefully tomorrow at the same time for hard disk reading. Ooh, exciting stuff. All right, good night, everybody. Bye.